Alright, so I believe this is recording. Let's take a look at solving these trig equations. This equation has infinitely many solutions. However, they're not wanting us to describe those infinitely many. They're just wanting us to list the solutions that are between 0 and 2 pi. They want us to give exact answers. We can use the calculator to check our work, but we can't give a decimal approximation with the calculator. We need exact answers. So we have this in one trig function, sine of x. Let's get on the left-hand side, I see two terms. The term that has our variable of interest is the first term. So let's get that term by itself by adding 2 to each side of this equation. And if I add 2, 2 minus 1 is 1. If I look now on the left-hand side, I have two factors. The factor that has my variable of interest in the sine of x, I want to get it by itself. So I need to, the inverse of multiplication is division. So I need to divide both sides by radical 2. So now I have sine of x is equal to 1 over the square root of 2. Well, I want to rationalize the denominator, because if I'm going to look at my unit circle and look for y coordinates, I'm not going to find one that's 1 over radical 2, but if I multiply this by square root 2 over 2, this square root 2 over the square root of 2, you're multiplying by 1, so the numerator and denominator have to be the same. And I have radical 2 over 2 because the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. You have these properties of square root that says when you have multiplication of two radicals with the same index, then you can just multiply what's underneath the radical. Even if it's square root, cubed root, or fourth root, or nth root, we have that property. Alright, so let's take the inverse sign of radical 2 over 2. The sine function agrees with the y coordinate, agrees in sine, S-I-G-N, with the y coordinate. This is positive, so we know sine is positive in quadrants 1 and 2 because that's where the y coordinate will be positive if you're above the x-axis. So in quadrant 1, I've got pi over 4. I've got that unit circle somewhere, yeah. All I'm doing is I've used the unit circle enough that I have it memorized. That at pi over 4, the y coordinate is radical 2 over 2. Well, also at 3 pi over 4, it's positive radical 2 over 2 as well, the y coordinate. So although there's infinitely many solutions, those are the two that are solutions to this equation that are between 0 and 2 pi. You could check that on a calculator. If we take the square root of 2 and multiply it by the sine, say we're checking the pi over 4, plug in pi over 4. Now don't forget to close the parenthesis. And then if we subtract 2, our equation says that we'll get a negative 1. Let's check and see if we do. And it does check. So if you wanted to check the other, you could insert the 3 pi over 4. And again, we should get negative 1. So those are checking. Now, it's possible that a student could make a mistake and leave out one of these, pi over 4 would check, and they accidentally leave out the other solution. That's the calculator's not going to help us if we lost a solution. Let's take a look at the next problem. This time, remember we have 6 trig functions. The ones that we're probably most comfortable with are sine, cosine, and tangent. The secant, cosecant, and cotangent, we typically will rewrite those using identities to be a sine, cosine, or tangent. But first, I recognized on the left-hand side there's two terms. the first term has the variable of interest x, so we isolate that term, we get it by itself. We're going to add 1 to each side of this equation. And we add 1 on the left, that cancels. We add 1 on the right, we get 2. Well, now we know that the cosecant and cosecant, I'm sorry, the cosine and secant are reciprocal functions. If I convert this to cosine of x over 2, then I have to take the reciprocal of 2, which is 1/2. Alright, now let's take the inverse cosine, and when we're looking for cosine on the unit circle, we're going to look at the x-coordinate, and the x-coordinate will be positive in quadrants 1 and 4, and if you'll find that x over 2 could be pi over 3, or that this x over 2 could be 5 pi over 3. Okay, let's multiply both sides, but we've got to get the x by itself. Multiply both sides by 2, and we get 2 pi over 3 and 10 pi over 3. Alright, now let's come back and look at this x over 2 for secant. See, secant and cosine both have a period of 2 pi. So when you have a coefficient that's different than 1, it's going to affect that period. Here we have this x divided by 2. To divide by 2 is the same as to multiply by 1/2. We have 2 pi divided by 1/2, and that's equal to 4 pi. So, you know, it's counterintuitive. It's not obvious. It's bizarre that when you divide by 2, it actually stretches the period. So normally, if you were expecting say 2 solutions on 0 to 2 pi, if you stretch that period, then you may lose a solution. You may lose, you know, both solutions. Depends on the problem. But if we rewrite 2 pi with a denominator of 3, that 2 pi can be thought of as 6 pi over 3. Well, you see that 2 is less than 6, but over here 10 is greater than 6. This is a solution to the equation, but it's not less than 2 pi. So they do not want this solution. It's too big. So the only solution that we have that's between 0 and 2 pi is this 2 pi over 3. Now, on my calculator, I don't have a secant button on my calculator. So if I want to check this answer on my calculator, I'm going to have to come down and check this cosine equation and just hope that I didn't make a mistake in converting this secant to a cosine. So I'm in radian measure because I haven't been changing that to degrees yet. I've got the cosine of x. I'm going to put my numerator, I'm going to put my numerator in parentheses just to be cautious. So I've got 2 pi divided by 3 in my numerator, and then that's being divided by 2. Close that, and let's see if we don't get 1/2, if we get 0.5. And we do. So that is checking, and it seems like our answer is reasonable. So let's move on. Now we have 2 terms on the left-hand side. The equation is written with only one trig function, the sine function. So I need to, my variable of interest is theta. I need to get this term by itself. Alright, so let's subtract 4 from each side. So we've got negative sine of 2 theta. And if I subtract 4 from each side, a negative 2. Now on the left-hand side, I have 2 factors. The factor of interest, the factor that contains my variable is the second one, this sine of 2 theta. So let's divide both sides by a negative 3. So sine of 2 theta is equal to 2/3, and this 2 theta is the inverse sine of 2/3. Now, when I go to look to my unit circle, and I look at y coordinates, let's go get that unit circle. You know, I do not see on these known points here, on these known coordinates, a y coordinate of 2/3. I need to pause this for a second. All right, so I'm back. So what do we have here? We have this angle 2 theta, and we're taking the inverse sine of 2/3. We look over here on the y coordinates, and we don't see a 2/3. Now, the decimal approximation of 2/3, is 0.6 repeating. 1/2 is 0.5. Radical 2 over 2 is, I don't know, 0.7 something. I believe that the point of interest, would be in there, and also a point of interest over here. So that's what I'm doing. Oftentimes you'll see me not go to the unit circle, but just simply sketch a circle, just to visualize what quadrant my angle is in. So I know that with this being positive, that there's a point in quadrant 1 that has a y coordinate of 2/3 on this circle, and there's also a point over here in quadrant 2. So I need to find these two angles, and I can't use my unit circle because it didn't have those values, so I'm going to have to use a calculator. Now the calculator is going to treat this relation like a function, and we've restricted the range for it to pass the vertical line test, and it's only going to look on the right half of this unit circle. And also, it's only going to return values that are between negative pi over 2 and positive pi over 2. Alright, so when I go to the calculator, it's going to give me this angle. So let's go and get that angle. If I go inverse sine of 2/3, double check that I'm in radians, and I get, let's see, it says round to the nearest thousandth, so let's go back. Oops, 1,000th is 3 decimals, and 0.73. Okay. Now, I need to figure out a way to get my angle that is over here in quadrant 2. The calculator doesn't give me this angle, but I can figure it out. This angle that's in quadrant 1, I can use that as its reference angle. That's the same, that measurement right there, that magnitude is the same magnitude of this angle right here. So what I can do to find my second answer, my second angle, is to take 2 theta, or to solve, take pi minus, what my calculator gave me from the inverse sine of 2/3. So if I do that, I've got pi minus that previous answer, at least to 3 decimals, I'm getting 2.412. Alright, now let's solve each of these for theta. Let's divide by 2. And divide this by 2. And alright, so I've got I'm listening to the Bob and Tom show. You can't hear it, but I hear it through my headphones. All right. Now, remember that there's infinitely many solutions to this equation. We're only looking for solutions that are between 0 and 2 pi. But we have to stop and think about what this coefficient of 2 is doing to the graph. It's actually a horizontal shrink. So we're instead of completing a cycle between 0 and 2 pi, this graph is completing a cycle between 0 and pi. So I'm going to gain solutions. So what I often suggest is that you describe the infinitely many solutions by coming in and taking 0.365 plus that cycle. Well, like I say, that the period, this new period for this graph is 2 pi divided by the coefficient of 2, which is pi. So we're adding pi n, where n is any integer, to get to the next solution. And over here, the same thing, 1.206 plus pi times n. All right, now, it's pretty well known that we can approximate pi with 3.14. If I double that, 6.28. So I'm looking for solutions that are between 0 and 6.28 if I have a decimal number and not exact values. So let's come over here on this equation and see how many solutions we can find in this interval. If n is 0, this 0.365 is bigger than 0. If we, where's my calculator? If I add pi to this, then I've got, when n is 1, I've got 3.506. If I add another pi, I'm at 6.6, which is too big. So I don't, if n is 2, this value 6.6 was too big, so I don't include that in my solution. Over here for this equation, we've got 1.206. When n is 1, we've got this 1.206 plus pi, 4.348. But if I add another pi, it's going to be too big. It's bigger than, well, if I hit enter, it's bigger than the 6.28. So I don't need to write that solution down. So I've got 4 solutions. With it just being theta, I would have expected 2 solutions, but when this shrank my period from 2 pi to pi, it introduced 2 more solutions on that interval from 0 to 2 pi. So let's list our answers. Boy, I've run out of room here. So I have 0.365, 3.506, 1.206, and 4.348 are my decimal approximations to the solution. Now, let's just go ahead and I don't know, we'll check the 1.206. Now, since it's an approximation, we may not get exactly 2, but we're going to expect to get something very close to 2. 4 minus 3 times the sine of 2 times my angle measure. Well, 2 times this 1.206. I should get something that's real close to 2 if that's a solution. Hey, I'm getting 2 to 3 decimals. And the same with these other 3 solutions and stuff as well. I could check on the calculator to see if that's a reasonable solution. It may not be 2 exactly for all of those because, like I said, we carried it out to 3 decimals, so that's probably good enough. If you wanted a little bit more accuracy, you could carry it out further. But there's our solutions to this one. Hope that helps, and I'll talk to you later.